Hello, in this lecture we are going to see one of our case studies, which is a Sokoban implementation. So the goal of this lecture is to think about how to model, in this case, a Sokoban, how to think about games also, and in particular, how do we use our knowledge on messages and conditions that we saw before. For this, we're going to study a Sokoban game. So a Sokoban game, for those that don't know it, it's a game where actually there's a player that has to push boxes, so like these boxes, into squares that have a target. Yeah, so the goal of the game is to push all the boxes into each of the targets. So it's a puzzle game. In this lecture, we are going to study an open source implementation made by students of the Ivan Franko University in Lviv in Ukraine. So thank you so much for your implementation that will serve us to study. So in this game, as you can see, we have the typical concerns of Sokoban. So we will have squares that are walls that we cannot cross with our robot. So we have a robot that we will move around. The robot will be able to push boxes into these targets. Yeah, and all these free places we are going to be able to walk around with the robot. So we will check the different classes implemented in the implementation we have. These are the main classes that we see. So we have blocks, we have empty block, and wall that are subclasses of block. We have a game model, a game state, a maze. We have a maze template. We have a move result, and then we have moves with subclasses like push, and then we have also a no move. So let's take a step back before going back to that design and think about what is the design that we would like to have in that Sokoban. Yeah. So let's use, for example, here one of the patterns in the Object-Oriented Reengineering book. So of course, you don't need to read the book to use this pattern, but of course, this book has a lot of other patterns that are interesting to see. And they talk about how do we take a look at an application that we don't know and how can we re-engineer it or even understand it without previous knowledge about it. So in this case, this pattern is a speculative design, and the objective is to think about the model, think about the problem that we are working on, and what is the possible design that is going to fit this problem without actually looking at the implementation. Yeah. So that is to use our expertise and our previous knowledge to try to come up with ideas on the possible design that we are going to have. Let's forget a bit about what I showed you before. We are going to compare it later, but take some minutes to try to understand what are the different classes that you are going to have in this game. So maybe you arrive to a list like this. So we have walls that will be representing these squares that the robot cannot trespass. We will have the floor that are the squares that the robot is going to be able to walk on. We are going to have boxes, maybe, like these boxes, the boxes that we are going to move. Then we are going to have the robot. Of course, if we are going to move it and draw it, probably a robot is a good object to have in this model. We are going to have the targets, or maybe you chose another name for it, but these little crosses here, it's the place where we have to put the boxes. And then maybe you arrive to the conclusion that we need to model also the board, so the entire game. Of course, maybe there is also the possibility, since I already influenced you with the previous model, that, yeah, maybe we want to model also the levels or having templates to be able to edit levels more easily. And of course, if we want to not only model the static part of the system, we also want to model how it works. Maybe we want to model the moves. If we go back to what we saw before, what we can see is that here we have three groups of model objects. So here we have, on the bottom, we have everything that is related to moves. So it's the dynamic part of the system. Then we have these four different things that are representing the game. So like the big board of the game. So there is a model, there is a state, there is a maze, there is a template, but all of them will represent similar things about the entire board. And then the smallest part of the system is representing actually the richest part of the system, which is the robot, the walls, the boxes, and all that. Yeah. So if we take a look at this, what we can see is that this model is it's a bit shallow. Yeah, so it doesn't represent the entire things or the entire all the objects that we saw in our model. So that means that we are going to have probably different cases. So when a robot wants to move on a wall, when a robot wants to actually push a box, when the robot is going to reaches a target, for example. So we are going to have different cases there. And if we don't have them modeled as classes, we are going to have them as tricky conditionals. So remember that the basis of object-oriented programming is to have different classes, to have different cases, because then we can use messages and classes to dispatch conditions. So instead of having a fat class that does a lot of things using conditionals, we're going to use a lot of small classes like this, and then it's going to be the dispatch, the message send, that is going to decide what is the operation that we are going to execute. Remember the lecture, for example, of implemented or not in Booleans. So if we go a bit deeper and we check the API of these classes, particularly the API of the boxes, we see that it has a lot of methods that are going to return conditionals. So these are testing methods. So they are, for example, there are the methods for asking if a block is empty, if there is a wall, if the block has a player on top of it, if it has a target, and if it has a blocks. And if we check how this API is used, we find methods like this one. So this is the method that will draw one block in the screen. Yeah. So it has to check all the potential combinations of the state of our model to be able to know how to draw it properly. So here, for example, it says, if it is just a wall, then it will draw a wall. Otherwise, it has to check if it is an empty block, so if there's nothing on top of it. In that case, it will draw, it has to check if it is empty but has a target, and then if it's empty and it has a target, it has to draw a target. Otherwise, it draws an empty block. On the other way, it will check if it has a player or a box. And if it has a player and a target, it has to draw a player, otherwise it has to draw a target, and so on. So it is a pretty complicated code, and it's fairly easy to make a mistake here. So if we analyze it a bit, so in a more higher level, what we see is that our model only defines empty blocks and walls, but there are no players, no target, no boxes, but those are important things for drawing and for also to actually to implement the behavior of our game. So that means that there will be too much logic in the empty block, because the empty block is the one that actually is representing the targets, the players, and the boxes. And this is also following a bad pattern, which is asking too many questions to the model. So here, we would like to follow this directive. So tell, don't ask. So instead of asking an object, okay, are you like this, are you like that, so I can take the decision, let's better tell the object to take the decision, because the object has all the information it needs to take that decision. So let's think, okay, what would be a better model? Maybe we could have an abstract superclass like tile. Yeah, so we could have a tile. And then we could have subclasses of it. And here we could see, for example, we could have a box. We could have a box in a target. That, for example, we are going to use it to draw it with a different color, because once the box is on a target, we know that that box is already matching the result of the puzzle. Then we could have, for example, an empty block that is going to represent a place where actually the robot can walk on. We can have player and we can have wall. Yeah, so at the end, the game is just a collection of tiles. And then, once we have a model rich like this, we can just send messages to these objects, and then each of these objects, they are going to do the right thing. If we want to replace this old and tricky implementation, one way to do it is to use our nicer model and to use delegation on the new classes that we are using. So we are just going to delegate to tell the objects to do something. So since now we have boxes or blocks here, that are going to be of different kinds, of different classes. So what we can do is to tell each block, draw yourself in this canvas. And then I don't know who you are, but you know who you are. So you know how to draw yourself. So then, for example, if we have a wall, the wall will have all the drawing of the wall here. And if we have an empty block, we will have all the code that draws an empty block in here. That will lead to actually simpler code in each part. And if we want to later replace one part of the system or even add new kind of blocks, we are going to be able to do it more easily. So that solution not only supports different kind of blocks, it also supports multiple canvases. So before, what we saw is that the application was being drawn in a Cairo canvas, which is a 2D API to do games. But instead, we could replace that with different canvases, like, for example, Morphic in Faro, or even an HTML canvas. So to do that, one thing that we can do is to not only tell the block to draw on a canvas, so we can send extra parameters. So here, for example, we can say the block, draw on this canvas, but I am going to send you the view. Like that, you can take more decisions. And here, for example, the wall can tell the canvas, the view, okay, view, draw a wall in this canvas. In this way, what we have is a lot of different blocks, as we saw before, and each of these will understand draw on for, and then they're going to send a message to a canvas, to a view actually, to a view that will understand how to draw each of the elements. Draw X, draw Y, and then the block is going to delegate the actual drawing to the view. And this will allow us to have different kind of views. So for example, we can have a Cairo view, or we can have an HTML view. So what we have seen here is an implementation of double dispatch. So that means that the decision of how to draw a block in particular is not only responsibility of the block, is the responsibility of both the block and the canvas or the view. So that is why it is a double dispatch, because the decision is taken by two different objects. So this shows how send messages is powerful and modular, because we can add now new kind of canvases and new kind of blocks by simply just extending the existing hierarchies. Now, let's take a step back and let's look again at these testing methods. So here we had this isWall and isWall method, both in wall and empty block, that were returning true and false in one case and on the other. So take a couple of minutes to think, okay, what do you think about these methods? Are they good? Are they not good? Are they useful? And so on. So every time that we see one of these methods, you could think that you are actually hiding some implementation details. So here, actually, this isWall is just a hidden way to write isKindOf or isInstanceOf in Java, which is actually a bad practice. One of the bad parts of this is that, of course, now this code that requires that the block is an instance of a wall, now it cannot work with other kind of walls. So all the walls that we implement, they need to be inheriting from wall. Otherwise, we cannot add new kind of walls that are not part of the same hierarchy. Otherwise, this test will be false. Now, if we go back to the model and we take a look at the other part, the dynamic part of the system, which represent all the moves, what we see is these objects that represent the actions that we're going to do. So we're going to move something. So we're going to move the robot up, down, left, or right. We're going to push a box if we move in some direction and there is a box in that direction. We're going to actually no move at all if we are trying to go in a direction where there is a wall. And then there is a result that, so actually all these are the result of trying to move. So I'm trying to go up, and then going up, if there is a wall, I'm going to have a no move. If there was a box, I'm going to have a push, and if there was nothing, I'm going to have a move. So these are representations or reifications of the actions of the player. And having them as subjects, they are not only good to be able to manipulate them, but also because we can store them, for example, to be able to record them later and replay the game automatically. If we take a look at the API of these moves, we see the same kind of pattern again. So we check, okay, so all the moves understand if they are move, if they're push, or if they are no move. So we are probably smelling that here we are going to see the same kind of pattern of nested conditions, which at the end are the same thing as asking, oh, is the class of this move this class or not? If we actually take a look at how they are used, what we see is that the game state is requested to move the robot to a direction. The direction is moving up, down, left, or right. And then the maze, which is the model behind, is going to give us, okay, if you want to move in this direction, this is the result. So here inside the move by, it is checking if in the direction that we want to move, we find a wall, a box, or nothing. And then what we are going to do is to, here we are checking if the move is a move or a push or something else. And then we count the number of moves and the number of pushes. And then we add it to a collection. So what is the problem of this? So here, the main problem is that if we want to add a new kind of move or a new kind of block that has a different behavior, we are not going to be able to extend it easily. So how can we do it better? Of course, the same solution as before is applicable in here. What we can do is to tell the objects to do something and not to ask them what they are. So instead of asking the move if they are a move or a push or something else, what we can do is to tell the move, update the game state. You know who you are, so please tell the game state what it should do. And then we send the game state as parameter. So here, for example, a move, it will just increment the number of moves. So the move will tell actually the game state to increment the moves. However, the push, we have a different implementation. It will do the same thing as its superclass. Remember that move is a superclass of a push here. And then the super will actually execute the one in the superclass. And besides incrementing the moves, because this one will execute this one, this message sending will execute that method, it will also increase the number of pushes. And then if we have a no move, that means that we couldn't do anything because there was a wall, we are just going to do nothing. So this is what this method does. As a conclusion, try to think about the classes that you are going to use in your model. Remember that little class hierarchies are good because they help you to do dispatch. Yeah, so the dispatch and the message is actually the most powerful thing that you are going to see here. So it is also in this same sense, it is better to have many small classes than a big one, because many small classes, they will help you doing dispatch and they will make it natural. Also, challenge this kind of testing methods. Every time that you see an is X, is Y, ask yourself if there was a better solution for that. And check their use. Maybe you will find a nest of worms.